A student of mass 72 kilograms running at 6.5 meters per second jumps onto a 35 kilogram sled. And right there, that's the sled. With coefficient of kinetic friction of 0.04. And it's an icy surface. The student sled system slides on the ice. What is the total momentum of the system before the student lands on the sled and immediately after the student lands on the sled? What's it going to be? Its initial velocity of the sled student system. Calculate the initial velocity of the system immediately after the student lands on the sled. Then find the kinetic energy of the system before the student lands on the sled and then immediately after the student lands on the sled. Was kinetic energy conserved during the collision? Explain. What is the total momentum of the system before the student lands on the sled? Well, the total initial momentum is going to be the momentum of the student. I'm sorry about the subscripts here, but ST stands for student. Didn't want to write the whole word out, but sled I could write the whole word out. So that's the momentum of the sled. So the initial momentum will be the student's momentum, and the sled's not moving, so that's a 0. So the initial momentum is all student. So it's the mass of the student times the student's initial velocity before he hits the sled. And we multiply the mass times velocity, and we get 468 kilogram meters per second. What is the total momentum of the system immediately after the student lands on the sled? And we have a lot of words there. And look, we're coming up with the same answer we had on the previous slide, the student's initial momentum. Why is that? Well, immediately after the student lands on the sled means that the student sled has just begun to move and it's not yet feeling the friction of the ice, which will slow him down. This is a perfect inelastic collision. In the absence of an external net force, which is the case here, momentum is conserved. We're not considering the friction force yet. The momentum after the student landing is the same as the initial momentum of the system. It's conserved, so it's 468 kilogram meters per second. Now calculate the initial velocity of the system immediately after the student lands on the sled. Well, we have a perfect inelastic collision. So we have the momentum of the student, the initial momentum of the student, the initial momentum of the sled equals their combined mass times the velocity of the student sled. Well, this term goes out because the sled's at rest. And then what are we trying to solve for? The velocity of the student sled right here. So we're just going to switch the equation around, then divide through by the total mass of the student and the sled, and hopefully this equation is becoming somewhat familiar to you. Plug in the numbers, and we find that their combined velocity is 4.37 meters per second. What is the kinetic energy of the student sled system before the student lands on the sled and is a true system? Well, we're going to use the kinetic energy equation. The sled is at rest, so the only kinetic energy is from the student before the student lands on the sled. So that's 1/2 mass of the student times the initial velocity of the student squared. Put our numbers in, being sure to square the velocity, and we get 1,520 joules. Now, what's the kinetic energy of the system immediately after the student lands on the sled? Well, we're going to use the kinetic energy equation, and we actually have the velocity of the combined student sled right here. And be sure you use here the combined mass of the student and the sled. Plug all the numbers in, and you get 1,022 joules. Was kinetic energy conserved during the collision? Explain. No. Our initial kinetic energy was 3,545 joules, and this was our final. It decreased, so it's not conserved. We expected that since kinetic energy is not conserved during a perfect inelastic collision. Energy, kinetic energy, was transformed into sound, some deformation of the sled, possibly, melting of the ice, and heat.